First, I will make a little disclaimer. I'm not the main author of ideas from this paper. The main author is Professor Vasyl Ustimenko, and he is the author of all the mathematical ideas and algorithms. My contribution was an attempt to implement some of these algorithms. The implementation is very incomplete as now. I implemented some building blocks of some schemes presented in the paper, and I will focus on my part on some aspects of implementation of this. I think I would have a hard time explaining every mathematical details because the description of these algorithms is on very high level of abstraction and highly theoretical. But Professor Ustimenko couldn't participate in the conference, and I will try explain. Okay, so maybe the first thing I will have I want to give some background, namely I will talk about two families of graphs. Algorithms in this paper are based on two families of algebraically defined graphs, on graphs defined with polynomial equations. And first, I will talk about some basic algorithms, and I will show why are not secure at all, and why are they broken, and then about some new algorithms that uses some ideas from these first algorithms, and but don't have the problems of the first. And I will talk a little bit about the implementation of some building blocks of these algorithms, mainly about the generation of some polynomial maps used in the schemes, and some discussion of number of monomials in these maps and generation time, and some discussion about efficiency and algorithms, some algorithms included. Okay, so first, the first graph family, DNQ. The background is from external graph theory. It's a graph family of large girth. It was developed by Vasyl Ustimenko and Lazebnik and Oldar, and it has some applications in cryptography and in coding theory. And the family of the graph is given this way. We have some tuple of n elements of finite field, of some chosen finite field. And we have two families of two sets of such tuples, one P and another L. This is bipartite graph, so we have two partitions, P and L, and there is a vertex. There is an edge between two vertices if the following equation holds. And the definition of families D and K and A and K goes this way. We have commutative, some chosen commutative ring instead of finite field, K. So the elements of tuples are from this ring. And for A and K family, we have different equations. Next, I must introduce the notion of color of vertices. The color of every vertex is its first coordinate, and if we look at these equations, then we can see that the vertex is uniquely determined by its neighbor and given color. If we take vertex and some color of then the neighbor of this color is uniquely determined. So we treat the walks in the graph as and some simple encryption tools. We take a start vertex and the sequence of colors. The colors are also elements of the ring K. And that uniquely determines the path and the last vertex. And in this simple algorithm, the plain text is the start vertex and the ciphertext is the end vertex. But this is very simple symmetric algorithms where plain text is the first vertex and the password is the sequence of columns. So then you have one path defined by the sequence of colors. And the ciphertext is the last vertex. If we look at the equations, we can easily find that the decrypting password is almost the same as the encrypting password, but in reverse order and with inverse elements. Okay, and it was simple symmetric algorithms, and then Vasyl Ustimenko proposed some asymmetric algorithms by representing these walks in the graphs symbolically, namely by computing polynomials generated by these walks. So instead of computing vertices numerically, we can compute them symbolically, and we can the ciphertext can be presented as a polynomial in terms of elements of the plain text. This polynomial transformation turned out that this polynomial transformation is a cubic polynomial transformation. So polynomial of the degree 3. And public information is the whole polynomial, and private information are three things. The first is the password and to affine transformation, which are applied to this transformation. One first and another last. So we get some kind of a polynomial map. And this scheme is one of the schemes that can be this kind of schemes are called multivariate cryptography. And it turned out that this scheme is not very secure because it's quite easy to invert this map, because the polynomial map is of the degree 3. The inverse map is the map of exactly the same kind, and it's also of the degree 3. So it's quite easy to construct some quite big system of linear equations and just compute the coefficients of this polynomial map. We have a system of linear equations with this much unknowns. Okay, so Professor Ustimenko took two directions of research of the graph-based algorithms. One was that some small modifications of this transformation could increase the degree of the inverse transformation, so we couldn't construct the system of linear equations, but without increasing the degree of encrypting transformation. And the second is using the low degree of inverse transformation to construct cyclic groups of transformations and use this cyclic group algorithms. So, for example, some versions of Diffie-Hellman and gamma and Diffie-Hellman key exchange and gamma cryptosystems. How can we construct such cyclic group? We can, if we take such map constructed from two affine transformations and one polynomial cubic transformations. Then, if we take these maps T2 and T1 such that one is the inverse of the second, then if we take some such polynomial transformation and we take the operation of the composition of these maps, then you see that the result is the transformation of exactly the same kind. So we have a cyclic group of polynomial transformation of degree 3, and these transformations are main building blocks of many schemes presented in the paper. I won't give exact details of all the schemes. They are really highly theoretical and abstract, and they are not already implemented completely. But I will talk a little bit about the generation of this kind of polynomials. So we have implemented 3 cases of such polynomials that differs on the choice of the affine transformations. They could be identities, they could be the map, very simple map of this kind, and the third case is affine transformation with full matrix and full vector with mostly non-zero elements. You can see that the number of monomials of such transformations does not depend on the length of the password. So if you generate such elements, we can and we combine them, then the number of monomials in such element doesn't grow. So we can quite efficiently implement it. Not very efficient, but quite efficient. So we can implement operations in the group. But the problem is that if we take generation time, if we take the length of the password of the fixed length and increase the number of variables, we can see that the time of generation grows quite fast. And this is one of the problems of implementation. One problem is that the description of algorithms is a very high level of abstraction, and we need to fill some gaps, choice of some concrete mathematical structures. There are some functions which can be chosen from some sets, and we have to choose which one to use. And the second problem is the efficiency. So the problem is with composition of polynomial maps, because this is the main operation in the group. It grows quite fast with a number of variables. If we have small number of variables, the order of the group is quite small, so the security of the schemes is not very good. But if we increase the number of variables, and the computational complexity grows quite fast. And the main the key factor in this implementation, in efficient implementation, is the implementation of the map composition, and the main building block of it is the implementation of a multiplication of multivariate polynomials. First, these polynomials are quite dense, so you can choose dense representation of the polynomials. And second, we know that all the polynomials are of no polynomial is of the degree higher than 3. So we can use truncated polynomials. So we don't have to care about the results of monomial multiplications that have a degree higher than 3. So the effect is that multiplication can be implemented in time linear on number of monomials. What I'm now trying to do, this is a work in progress, is to employ some high performance computation techniques in the implementation of these operations. First, we have dense polynomials, so they are stored in arrays. We can construct algorithms and that data structures are such that they are cache friendly. So if we load to some part of this polynomial to the cache, we want the algorithms to use these elements as much as possible. And the second thing is to use parallelization in the implementation of this operation. Okay, and that's all. Thanks for your attention.
Thank you for the presentation.